So the week by week thing here, I'll put it into student view so you'll see what it looks like from you. This is where I'll plop the lectures because I'm going to record them just like I'm doing now. So today's recording will show up just under the day that it was done, right? So I just set up a week and then the 3 days. Sometimes I won't put Friday in because that's quiz day kind of thing. And there won't be a lot of content on Fridays. But Monday, for example, has Monday stuff in it. Sometimes there'll be some data. Most of the time, it's just going to be the recordings, the lectures from class. So if you miss a class or can't come, you can get the recording. The syllabus is here. Let's see if we can open it. You can look at that briefly. You should look at all your syllabuses. I don't know about reading them top to bottom. I don't know about that. But you should look at them and find the important information, like if there's an attendance policy, you should look at that. I don't have an attendance policy. I don't grade on attendance. You'll come if you want the information. You won't come if you don't want the information or you can't come, kind of thing, right? The first week I have to take attendance just for this mandatory attendance thing. So we find if people are coming to class or not, I guess. You can look through all this. There's 2 exams in this class, a first and a second. We'll do it around week 4 and then again around week 7. Okay. There's a good breaking point between chapter 4 and 5. So we'll do it after chapter 4. And those will just be in class and we'll schedule them. We're getting close. But the other thing you should look for is just the grading schema in your classes. So you know how you're being evaluated. So if you don't do anything else, when you get the syllabus or have access to a syllabus, of course, look up the attendance policy because you could be getting hammered if they grade on attendance and you're not coming, right? That sucks. You're an A student, but you didn't go half the time and that dropped you to like a C student because somebody's weighting attendance crazy. So just check that. And then look at how you're being graded. So ours is 20% quizzes. We have 2 midterms. They're each 15%. Homework is 20%. So it's important, but it's not. If you miss a homework, don't stress, right? If you miss 5 homeworks, then you start thinking about that's going to impact my grade. Usually there's 2 extra credit homework assignments through the term. So if you miss 2 and you do both the extra credits, you're still 100%. Okay. So some students get really stressed out when they miss a homework set. Don't. You should still do it because you're going to need that knowledge. But if you miss 1 or 2, you're fine. And then the final. Is that up to 100? 50 and 50. Yep, that's good. Questions? Pretty straightforward. It's called weighted grading, right? But quizzes are important. They're 20%. So if you've done the homework during the week, like this week will be 2 homework sets before the quiz. If you've done those 2 and you're comfortable with them, you'll be fine on the quiz. So it's when you get that homework set that you're not comfortable with, like, oh, that didn't go so well. Like, I just couldn't do it. And then you don't get that problem solved by Friday. That'll show up on the quiz. And then you'll be in that same boat. So don't do that. Don't do that. Oh, that's not what I want. And then in the grade area, I think there's a lot showing up still here that needs to be just taken down, but you should be able to go into here and see your grade at any time. So I'll be grading this as we go along. So keep an eye on that. That's it. That's Blackboard-ish stuff. Yeah, questions? Okay, good. All right, let's talk about the class itself. We've talked about the book a little bit. If you just came in, there's a few of the books that people have. We're going to do homework out of the book today, and I've scanned that into Blackboard. So you should be able to see the homework sets in Blackboard. I'll show that again. It's here, week 1, Monday, and at the bottom it says scan a book. So I think you're going to do 2, 4, and 5. So you gotta ignore the rest of this markings, because that's just years of markings. 2, 4, and 5. It's trigonometry. Eight to 10, Monday, Wednesday, Friday. Lecture will be kind of around probably 8:30. From 8 to 8:30, we'll go over the homework. So the homework you're gonna do tonight, Wednesday, we'll go over that first thing. So the deal with that is, we want the homework done when you walk in, right? And then it's in front of you. But I do want you to write on it. Like if you've done something wrong, I want you to correct it. And that's for your knowledge, not necessarily for homework points. So when we go over homework, you need to have a different colored device in your hand. So when you make notes, I know those are the notes you made in class. Okay. We should work our homework in pencil and then have like a red pen. Red's so negative. Have a green pen for your comments on your own homework. So what that does is you've struggled with the homework, you've done your best, you think you got it right, and then you come in and then I show like how it's done correctly, and you're like, oh crap, I did that wrong. That's what you should be writing down on your homework. Then when I get it, I give you a grade, I give it back to you. You have not only your work, but the corrected version on your homework to look at. That process is extremely good learning. So the 3 like rungs of learning should be, you read the book, you read some content there, you do the homework, you come in and you get a lecture on. If you're doing all 3 of those, you will get the content. That will come. Some of us get that content just by sitting in lecture. I went to school with a kid that could just sit there, not take a note. And literally, he had it. I was like, what? There are people like that? That's not me, right? So you have to figure out like what works for you. Most of us takes all 3, by the way. All right. So that's how we'll do homework. Let's talk about the homework format. So I prefer green paper. You don't have to have it on the first one, that's fine, or the second one, just maybe by week 2, you have some kind of engineering comp paper, right? This is preference, but if you have any grid paper, if it's white, I don't care. But a grid paper is super nice to work on for making sketches, for doing calculations, for all kinds of things, okay? So prefer this, but any kind of engineering comp paper will work. You're gonna need a calculator, right? Some kind of calculator. The calculator that you know how to run would be the calculator to get. Don't go buy something fancy and new. You don't need an HP just because I run an HP. If your math classes are using TI, then get a TI and use that, right? But we do need one, and we need it up and ready to go pretty much every day, because I don't like to calculate stuff in front of class. I'd rather have you doing that and give me the number, right? Now and then I'll get frustrated with you and I'll just calculate it myself because I want it faster. Or you won't all agree on the number or something. So, but it's really good if you have one going and ready to go. So that's helpful. The format is pretty straightforward, but I want us to follow it. So if we can all do that, then I'm going to look at all your homework every day and I'm going to give you feedback on it because you're going to do it and that's the best way to learn. But I need it all coming to me kind of the same way. So you need your name on it. That can be anywhere in the upper area, and I need a class. So I need statics. You can just write ET221 if you want. You can write statics. But if I get this in a pile that's not statics, then I know right away, hey, that's a statics assignment. I can get it in the right pile, right? If you give it to me late, walking down the hallway or something, then I know, hey, it's got a title on it, right? It'd be great if there was a date. Notice I'm trying to print, and I am using a pen, but that's because it shows up really. If I use pencil here on the overhead, it doesn't show up worth a darn. So yours should be in pencil. And then something like 1 of 1 or number of pages. So if the stapler is out of staples, which it normally is, and you turn it in, I can see the first page says 1 of 4. I should be able to find 4 pages, right? If it says 1 of 1, then I know I got everything, right? So number of pages is really good. Then we just start into problems, and it's helpful if you label them chapter 1 like number 2. Right? So the chapter is fairly important to me because if things are not coming in at the normal time, I can get them again into the right category and I know kind of what to look for. Then we need a problem statement. So the problem statement can be abbreviated. It doesn't have to be word for word out of the book. The book could have, if you look at a problem out of the book, it could have, 2 paragraphs of information. I don't need that. I just need to know what the problem is you're trying to solve. So you can abbreviate it, but I do need a problem statement. So I'm just going to make this problem up. This is not going to be number 2 out of the book because I don't have the book, right? We're just going to make up something. You can do number 2 if you want, but I'm going to say solve all parts of a right triangle. So that's the problem statement that I get out of the book. Almost every problem is going to have some kind of graphics. So I have this really cute little triangle that I just carry with me all the time. It goes in my calculator pack, right? So if actually I'm anywhere and I need to draw a little sketch, I can do a little straight edge thing. So straight edges are nice for sketching. So then whatever's given, you're going to put down that information. So making a decent sketch is important. Some folks actually write given. That's very academic because in the workplace, you're not going to write that. You're just going to write down the information that you know, and then you're going to try to solve whatever problem you're trying to solve. But I think in the homework format that's on Blackboard, it says given, right? So problem statement, given, solution, that's what we're looking for. The flow is kind of top to bottom, left to right. It doesn't have to use a whole piece of paper, right? You don't have to do 1 problem per paper. But don't jam 8 problems in 1 piece of paper. That's really hard for me to process. So just keep it kind of comfortable. So now I'm going to write, this is 6 feet. And this is 4 feet. And this is a right triangle, which means what? It means there's a 90 in there somewhere, right? A right triangle has 90 degrees in it. All right, so then this is saying just solve all parts to this triangle, right? So we need to label the triangle. So this is chapter 1 where it's talking about trigonometry. So if you've not seen trigonometry in a while, you might want to read chapter 1. If this is like, oh man, this class is going to be super easy, then that's a good thing. That means you've had right triangle trigonometry somewhere. All right, so labeling them, the angles typically are capital letters. Right, and they're A, B, and C almost always gets the 90 degrees. Now, the triangle could be labeled a number of different ways also. You can label it any way you want, or if the book labels it something different, label it the way the book does it, because then we'll all be able to talk about the problem, right? If you label it differently and someone says, hey, I'm working on angle A, and you're on the phone with them, and they're like, I don't have an angle A, pretty nice. Now we have chaos, right? So just label it the same. And then the small sides are lowercase, and I try to put a tail on my C for it to be lowercase. And then this would be B, and then this would be A. Because opposite sides, right? Opposite angle A is going to be side A. Opposite angle B is going to be side B. And I'm going to take my time with trigonometry because this has got to be like that for you. In other words, after today, I don't want to have to explain right triangle trigonometry, right? So I'm going to really take my time and go through it. And if This is boring, that's good, that's a good thing. This is not boring, and you've not seen this in 100 years, then we got to try and bring it back to where it's pretty comfortable. And one of the fundamental concepts of right triangle trigonometry is this opposite of thing, right? So here's angle B, the side opposite is that. And it's important that you can see that, because most of our trig functions work off of this opposite and adjacent thing, right? So we have to know opposite of what? It's not always the same side. Like, what's opposite of A? It's side A down here. What's opposite of B? It's side B over here, right? So it's dependent on where you're sitting, where I'm thinking about. If I'm thinking about angle B, then what's opposite? It's this thing over here. So that's kind of fundamental. All right, so here's our opposites. What are our tools for right triangle trigonometry? Give me all the tools. SOHCAHTOA. Love that. Okay, I'm good with that. What's that mean?
Sine.
So that's the trig functions, right? It's sine, cosine, and tangent. Super important that you understand this is only for right triangles. This is not non-right triangles. In other words, if it doesn't have a right triangle in it, you can't use these. They don't work. But these are good for right triangle trig. So what does sine of an angle equal? SOHCAHTOA tells you that, right? That's how do I spell SOHCAHTOA? SOHCAH. See, I don't do that thing, but I hear it all the time. So I get it. I think sine is opposite over hypotenuse.
Yep.
Yeah. Cosine is adjacent over hypotenuse. Yeah. So that's how that thing works. That was a lot. Oh yeah, then there's the next one, right? Yeah. So what this is giving you is a way to remember the functions, right? You don't have to memorize stuff in this class. Not a thing. You just have to be able to use it, figure it out, okay? So for example, the quiz on Friday, I'll have the trig functions on the quiz. Sine equals opposite over hypotenuse. Because I don't need you to remember that. You can look that thing up if you can't remember it, right? So memorization is not a thing that I need you to be able to do. I just need you to be able to run it correctly. Yeah, yeah. So this is sine is opposite over hypotenuse, correct? What's the hypotenuse? The long side across from the 90, right? So it's C. That's the hypotenuse. Longest. What's opposite? Trick question. What is the opposite?
That's the opposite side of the angle that you work with.
Thank you, Jorge. So we got to know what angle we're working with to know what opposite is, right? So if I'm doing the sine of B, angle B, then the opposite is side B. Yeah. So this just sets up the relationship, but it doesn't tell you what sides to use because you haven't put an angle in here. I just put theta in there. That's the Greek letter theta. What is that, an O? No. I don't know what theta is. I know what alpha is. Alpha is an A. Gamma is a G. What's theta? Must be like an O. That's a delta? No, that's theta. No, delta is, what is delta? Well, that's, don't be challenging my theta, man. What's this? I thought it was rho. Is that phi? Oh, boy, we got to get our Greek letters down because engineering is all about these Greek letter things, right? All right, that's my theta. All right, good. And then this one is what? Cosine. Adjacent over hypotenuse. I didn't use an HYP as hypotenuse. And then what's tangent? Opposite over adjacent. Okay. This is like the key to life, in case you were wondering. Maybe you've been going to church, but that's not it. It's this. All right. So now how do we use it? Like, okay, we use this to solve this, right? What other rules do we have? These are good. Yeah, a squared plus b squared. What's this thing called? Such a great name, Pythagorean theorem. Yep. And what are all these? A, B, and C? Sides. Yeah, they're sides though, right? So this is a relationship between the sides of a right triangle. Really grinding on that, if you haven't noticed that, because this doesn't work in a non-right triangle. Don't do it. Doesn't work. We're just talking right triangles here. Excellent. What other things do we know about right triangles? There's one other. Internal angles equal 180. So the sum of the angles equal 180 degrees. So if I know two angles, I can get the third angle by subtracting from 180, right? It's huge. These are all our tools to solve these things. Why the heck do we spend time with triangles? Anyone know that answer? Hmm?
Because everything you can solve it with a triangle.
So we do a lot of triangle work, like we build structures out of triangles. So the next bridge that has a structure that you can see, look at the structure and you'll see a bunch of triangles, right? You look at roof trusses, bunch of triangles. If you think about forces, which this class is going to think about a lot of forces, we're going to represent forces as vectors, and we're going to put vectors together to understand the combination of forces, and it's going to build a crap load of triangles that we then have to be able to solve. So we have to get like really good with these triangle things because we're going to use them for everything. All right, excellent. All right, so now let's solve this thing. We know one side is 4, one side is 6. We don't know those angles. We know it's a right triangle because I put this little 90 in here. That brings me to assumptions. Make them. If you need to make an assumption, make it. So if they give you a triangle and it looks like a right triangle and you're doing right triangle trig in the chapter, you might want to just assume that's a right triangle. They just didn't tell you that, right? If they give you this, then that indicates it's a right triangle. But like on the homework, if you need to make an assumption, make it. Note it, write it down. I'm assuming this to be a right triangle and work the problem. And I'll look at it and go, oh, that was a bad assumption, but you did it right, so nice job. Let's go on, right? Or that was a good assumption, whatever. But note them. All right, so how can we solve this? Any ideas? We can do the Pythagorean theorem to get C. Is that what I heard? How else could we do that? Is there any other way to get C? Yeah, you could get an angle first and then work your way to C. So there's a lot of different ways to go after it. So there's not just one way to do it. You're not going to always just be able to do Pythagorean theorem. What if we just had one side and an angle? Then we can't do Pythagorean theorem, right?
Give you the
So yeah, we can use tangent and get angle A. That's opposite over adjacent. We know both those, right? So the point is you have all these tools, but you can't just, sometimes I see students that are just like, oh, right triangle, I'm gonna do the sine. Like, no, you can't always just do that. Like, what if you don't have opposite and hypotenuse? You can't do the sine, right? So you have to look at all the little tools that you have, and then you have to say, oh, I can apply this one because I know enough, right? If I wanted to run the sine of angle A, what would it be? The sine of angle A.
so
Just tell me what it is. It's opposite 4 over C, right? Do I know angle A? No. So doing the sine of angle A is not going to work. Does that make sense? Yeah. What about the sine of B? 6 over C, and I don't know angle B, right? Not going to work. Get it? Get the point there? All right, so we have to look at what we have. I heard Pythagorean theorem, let's do that. So I'm gonna write Pythagorean theorem as 4 feet squared plus 6 feet squared equals c squared. Right, just plug an A and B in to the equation. That make sense? Everyone okay with that? Right, but I chose Pythagorean theorem. So you're gonna choose, you're gonna do it all different ways, but I heard this one first. So we're gonna do that to solve C. How do I solve for C? Yeah, so we have to do some algebra is what we have to do. And that's the other big thing about algebra. Our big thing about statics is algebra. We have to be able to understand and remember our algebra, how to isolate a variable. We're going to have a lot of variables in some very complicated equations. This one's not too bad because this is what? 4 squared is a number, correct? 6 squared is a number. So we can just get those numbers. And then what do we do with the c squared to get c by itself? Do the square root of it. So if I do the square root of one side, here's the key to algebra, if you haven't learned this. What do I have to do to the other side?
Same thing.
Same thing. That's algebra. That's pretty much all you need to know about algebra. What you do to one side, you got to do to the other side of the equation. End of story. Right? So if you have a variable, you need to get it by itself. And if that means dividing by 4, then you got to divide the other side by 4. Just what you do to one side, you do to the other. So here, this is going to clear that into just c, right? The square root of c squared is just c. And then here's my number over here. Yeah? All right. What is that number? Somebody crunch that for me. No, I want that number.
7.1.
I like it though. Great question. Give me the number. What's the number?
7.21.
72111. That's good enough. And then what's the unit of this? Yeah, so we have feet squared and feet squared, right? And we added feet squared. We can do that. It's like 4 apples and 2 apples, 6 apples, right? So as long as the unit's the same, you can add them. And then we took the square root of it. So what's our unit? Feet. All right, well, let's talk about precision, which is what Jorge was asking. Like, hey, how accurate do you want this number? Or how precise? So we're going to go with engineering precision, not significant figure or mathematics precision, which just doesn't work in engineering. So it doesn't matter whether the number starts with a 7 or a 0. The precision is based on the accuracy of the numbers we have, right? If I am accurate, 6 feet is accurate to thousands, 6.000, then it's accurate to thousands, right? And if this is accurate to thousands, then that is accurate to thousands. So we cannot be more accurate than the information given to us. That make sense? So if I say, well, how long is that beam? And you take a tape measure and you measure it and say, oh, it's 84 inches. Then I got to go, you used a tape measure. Like, is it 84, like spot on perfect or within a 16th or what? You know, what was that number? What's that accuracy? So really the only way you can reflect the accuracy of a calculation is knowing the accuracy of the numbers. So in academics, we don't know the accuracy of the numbers. Like, we're just giving these numbers out of the book and they're just going to come to us, right? We don't know. So we have to make an assumption about the accuracy right away. So in this class, I would like you to make the accuracy assumption of hundreds, 2 places. Any number given to you is accurate to 2 places, unless it's given to you in 3 places or 4 places, right? If it's given more accurate, then it's more accurate. And then we're going to go with the least accurate number in our calculation. So trying to keep it simple, not complicated. every number that comes to you is accurate to two places. So that means any number that you produce is at least accurate to two places. Make sense? So that just identifies our precision. When you get out in the workplace and you're running a strength of materials calculation, you need to know the accuracy of the numbers you're running, right? So if you're using like a modulus of elasticity of a steel, you need to know the accuracy of that number. Like somebody did testing to give you that number, you should be able to find the accuracy of that. So then you can kind of keep your accuracy in line. So this would go to what? 7.21 feet. All right, so this is kind of a homework flow. I would love to see the equation you're going to use. Do you have to list them all? No. But I'd like to see the equation you're going to use, and then I'd like to see you use it. So I did that. Here's my equation I'm going to use, and here's where I did it. Right? So both of those is nice. Within the equation, I'd like to see your units. So don't just leave the feet out of there. I'm okay with these marks for feet and two little marks for inches, but you can also just write feet, right? Your unit analysis will save you when these problems get difficult, because you should know what unit you're trying to get. Like, okay, we're calculating a side, right? We should end up with feet or a length. And if you're not ending up with that from your unit analysis, then something's wrong. There's a mistake in there somewhere. So really important that you keep your units within the equation. In the end, I'm going to want you to commit to the solution. And committing to the solution means something like this: underline, double underline. In other words, I don't want to see four numbers and try to figure out like, oh, which one did they really think was right? Sometimes I'll see like, it's this or it's this. Like, nope, which one? Like, let's commit. What I do is I do a double underline and I stick an arrow to it. So you can do whatever you want. You can put flowers around it or make it yellow highlighter or however you want, box around it, but commit to your solution, whatever you're trying to solve for, right? So, and then just full disclosure, one of my ways of correcting things is to go straight to your solution and see if it's right, right? And if it is right, then I'll just go scan back up and see that the work makes sense. If it's wrong, then I can work my way back and try and figure out where you went wrong and fix it. The odd numbered problems, the solutions are in the back of the book. The odd numbered problems, okay? And I'll give you both even and odd. The solution's super valuable. Work a problem, like it, right? Feel good about it. Look at the solution and it matches. Boy, we're just like so happy. Do the same thing, look at the solution and it doesn't match, and we're like sad. Like, damn it, what'd we do wrong? Kind of thing. I can tell you that the solutions in the back, there's a couple of them that are wrong. So that's really discouraging. So don't get too wrapped up if your answer is different than the back of the book answer. Precision wise, it could be a little off too, because the book does its accuracy a little differently. So just be aware of that. Is this good? Homework format, okay? And then you could start another one. You know, I'd probably draw a line, but you wouldn't have to. And then I could go chapter 1, number 4 type of thing. And just work another one right here. Right? Any questions on that? All right, so there'd be more to do here. I didn't get it all done, right? We just solved for side C. Now, how could I get A? Angle A?
4 divided by 6.
Using the tangent, 4 divided by 6. I like that. Why do I like that? Man, maybe. It's not using the number I just calculated. Does that make sense? Like if I use sine, I got to use opposite over hypotenuse, and I just calculated that. If it's wrong, I'm screwing up the rest of the problem. Or if it's not accurate. Like if I put 721 in my calculator, that's not going to give me a good number. In other words, when you go back and use a number, you want to use the whole number. If you're going to recalculate with things that you've calculated, don't use the rounded number. You got to go back and use the whole number. So that's a little more work, especially if you're not good at storing numbers in your calculator. I store, right? So this thing stores 15 places. So I'll just store numbers as I'm working through, and then I don't have to worry about rounding at all until the very end, right? And then I round. But then my numbers are stored and I can go back and use numbers, and it's pretty simple. But if you're not doing that and you're gonna retype in a number, go out at least 4 places and you'll be fine. You don't have to get all 15 in there, right? But go out 4. But I like Jorge's idea of using tangent because it uses the 2 numbers given in case I mucked that one up. That makes sense? Yeah, so I could use tangent for that one, and then B, I could use tangent for this one, opposite over 4. Let's write one of those, just so we remember how to do it. So if I said, I want to know I want to know A, so I'm going to write tangent of A is opposite 4 feet over 6 feet, correct? Opposite over adjacent, did I do that right? I think so. Opposite over adjacent. 406. Okay. So in this, what am I trying to find? A, angle A. Seems obvious, but I just want to make sure. Like if you're running this and the variable's there, you're trying to find an angle. So what kind of units should we get in the end? Degrees or radians? Which one? Trick question. How do you know? Not if your calculator is set to radians. The calculator is not going to give you radians, right?
Yeah, but that
Yeah.
point is.
No, the point is, right, if your calculator is set to degrees and you run this, you're going to get degrees. If your calculator is set to radians, then you're going to get radians, which is a little bit of a wacky number, right? Remember, there's 2 pi radians in one circle in 360 degrees. So we will use radians at times. There's a few formulas that we run that require radians, which is kind of weird. But most of the time, we just want degrees. But the point is, when you're working a problem, think about the unit that you want out the end. Like I'm working this. I want angle A, I need degrees out the end, right? What approximate is the approximate solution? What's your guess as to the angle of A if you haven't calculated it yet? You think it's 80 degrees? No. You think it's 1 degree? No. What's your guess? We're estimating here, right? We're looking at that angle, and what's our estimate of that angle? Yeah, somewhere 45. What would the 2 sides be if it was 45? No, they would be equal. They'd be equal. So if they are equal, we got 45. Are they equal? 4, 6? No, they're a little, I mean, it's a little smaller up here, right? So I'd say it's less than 45. It's a good idea to do this, to estimate what you're looking for. Because if your solution's coming up with 0.4 degrees, like what? That's way wrong. We don't even want to write that down, right? We're looking for somewhere in the 35 to 40 degree to 30 degree range here. And I know that because my little sketch is approximately to scale or proportionate, right? So when you make your sketches, make them kind of right. Make the 4 smaller than the 6, right, in the triangle, and it'll give you an idea of what we're looking for solution-wise. All right, how do we solve for A? Okay, that's the professional way of doing it. What's the beginner way of doing it? How do I isolate A to get it by itself? What do I got to do? What do I got to do to get rid of the tangent? Divide by it. Yeah, divide by tangent. What happens? Boom, I'm done. What I do to one side, I have to do to the other side. So I got to take this whole thing and divide by tangent. Tangent in the denominator is the same thing as tangent to the -1, which is a common way of writing this thing, right? Tangent to the -1 of 4/6. The other way of writing it, you'll see, is arctangent, which is, I think, what Samuel said, right? Arctangent. So on my calculator, you can see right there,
Right, I have a question.
it's noted as a tangent. That's the arctangent function. Or the 1/2. Yeah,
Question for all, do you want all like that, or you want the basic, explanation of the corporation?
this is good right here.
Right,
Yeah, so you can just have the formula and then you can just give me the solution, right? And as soon as I see that's getting mucked up, I'll put a note and say, you gotta start writing the formula out because you're screwing it up, type of thing. But I don't need to see it. I just need to see this
right.
and then A equals. Gina, did you have a question? You had that question look.
No, I was wondering, because you obviously know it's gonna be like arctangent, like could you just write that, or do you want the formula with the division?
This,
Okay,
either one's good. Yeah, I don't care. So you're saying like, instead of just writing that, you could just write this. Yeah, no, I'd be good with that. Yeah. Yeah. Good. All right, what do we get for a number?
33.6.
A equals 33.69
69.
degrees, thank you. All right, so let's talk about angles a little bit because there's a few different angles of 33.69. Now, remember, we have this graphic along with the work, so this is probably good enough. Right? Like I can put that together in my head, like, oh, angle A is 33.69, angle A is right here. Right? So there's other ways to do that. Sometimes we'll see this notation, positioning that angle. Right? And when we get to vectors, this is super important. I need to know what position your 33.69 is in, because it could be here. Right? I mean, it can be in a lot of different places. It could be here. All of those are representing little symbols that could represent the 33.69. Right? So we have to think about, like, where is the 33.69? We have this graphic, so we're good. We don't need any extra notation. But when we get into vectors, we're gonna need to know where that vector is. 33.69 from where? From vertical, from horizontal, from the horizontal negative quadrant, from the horizontal positive quadrant, you know, we're gonna need to know where it's at in space. Okay, excellent. What was the whole number? 33.6.
6901.
6901. So we rounded perfectly. Good? All right. Let's take a break. So first day, I probably will talk for close to 2 hours just because we're gonna cover some more stuff. But I like to take a break, so we'll do 10 minutes. We don't have a clock anymore, so I can't say the big hand on the whatever. But I have 8:53, so something like 5 after. Does that sound good? All right, break time. So what's given?
The angle and the hypotenuse.
Yep, and our C value of 20 feet. Right? So we're looking for something that uses an angle and a distance. All of these have angles in them and distances. So these could work, right? We don't have two sides, so that's not going to work. And we only have one angle, so that's not going to work. So you just kind of pick through and decide what you know and what fits. So what does fit? We do have two angles, couldn't we? Could go for this. Yeah, so you could calculate that third angle. Yeah, 63, somebody did it. 180 minus 27 minus 90, right? All right, so now we have more information. We have another angle of 63 degrees. What'd you use to solve it?
Sine.
Yeah, sine works. Sine of the angle that we know, 27 degrees, is equal to opposite h over hypotenuse 20 feet. So when you know the variable or you know the distance, put it in the equation, right? So instead of writing opposite, I write h, because that is the opposite side to the 27. I know c, so you put it in, right? If you've chosen a function or a formula correctly, it should have one variable in it. If you write it out and it's got two variables, then you don't want to do multivariable algebra yet. We'll have to do that at some point, but not yet. All right, so how do we solve for the h?
By sine of 27 by 20.
Correct. What Jorge is saying is multiply both sides by 20 feet. That's the algebra, right?
Oh.
The way you clear this is multiply by 20 feet, and that 20 feet is over 1. And I'm just showing you long form. You don't have to show me this. Like if this is intuitive to you, that's great. But I find that algebra just sneaks up and grabs us and it eliminates the problem, which is not good. So what I do to one side, I gotta do to the other. Gonna put the 20 in here and multiply it by the sine 27. H is now by itself, so it ends up to be h equals sine 27 degrees times 20 feet. I got my units in there, right? Should be good to get an h number. What'd you get?
9.08 feet.
Everyone agree? 9.08 feet. It's good. All right. Excellent. Questions? All right. Let's look at this problem. "30-foot ladder, we have 27 degrees up here, and then we have some kind of irregular ground, which I'm gonna go ahead and just put the rest of the triangle in, right? What kind of a triangle is this? It's not a right triangle. I don't really care that you know whether it's an acute or an obtuse, but it's actually an obtuse because obtuse has a larger than 90 angle in it. If it's all smaller than 90, it's acute. But I don't care that you know. All I care is that you look at that and go, oh crap, that's not a right triangle, right? So all of this strategy, except for one of these, all of this is not valid. Which one is valid? Yeah, the 180. The 180, not the a squared. No Pythagorean theorem. No sine functions. Okay? We have other laws. What laws do we have? We have the sine law. How do we write that? Anyone remember the sine law? Oh, this is the good stuff now.
For sine of A.
Uh,
B over sine B.
Yeah. What he said. That is the sine law. It can be written that way, or you can inverse the whole thing. Like you can write sine A over side of A, sine B over side. These are sides. These are angles, right? Sine law. There was more. What was that other law? Cosine law. What's that one? C squared equals A squared plus B squared minus 2AB cosine C.
Can't remember that.
Yeah, I know. You don't need to remember it. That's the good news. It's in the book, and then it's right here. That's C squared. I got a little sloppy here. C squared equals A squared plus B squared minus 2AB cosine C. So these laws are what we use for non-right triangles, non-right. And the combination of the angles is helpful too. Now, the sine law, you don't use all three pieces of the sine law, right? There's 1, 2, 3 pieces. You use any two pieces of the sine law. So the sine law would operate like this, or potentially like this, or then maybe just these two out here, right? We only use two portions of the sine law at any one time. That means you need to know three things, because there's 1, 2, 3, 4 unknowns. If you're just looking at two of them, right? 1, 2, 3, 4. That means we need to know three things about the triangle in order to use the sine law. Okay, now the cosine law has 1, 2, 3, 4 variables. Has side C, side A, side B, and it has angle C. 4 variables in the cosine law. That means you need to know three things about the triangle. So in both cases, you need to know three things. This one, you need to know either two sides and one angle to get that angle, right? Or you need to know two angles and one side to get that side. So if you have 4 variables, we have to know 3 of them so we can solve for the single unknown variable, right? Both laws are the same. They have 4 variables. We got to know 3 things. So if you only know 2 things, you're just stuck. That's a problem. So you can, hopefully they don't give you that, right? But if they do give you that, there's probably some way to find something else out somehow, right? I've given you what? 30 feet for the long side, 27 degrees here, and that's it. That's all I gave you. That is only 2 pieces. Correct? It's 2 things about the triangle. That's not enough. Does that make sense? You're not going to fill in either one of these with just 2 pieces because there's 4 unknown in each equation. You got to have 3 things known. So this point, let's say is, I don't know, let's say we measure this and it is, what do we got here? 30 degrees. I don't want this realistic. I don't know, we'll say it's 8 feet. So now we have our third piece of information. We want to know H. Okay. So we know 2 sides, correct? And 1 angle. 2 sides and 1 angle. So 2 sides, 1 angle. This could work. Some kind of a sine law function. All right, so let's look at that. Now, these are opposite of each other, So, and I know 27 and the 8, that's the other thing that you want to look for is like, do I know information opposite of an angle? Because that means that this is a known, it's a known number. Okay. So I should be able to say, okay, 27 and 8 is maybe my A. And again, A, B, and C, you don't have to get too wrapped up in that. C is the long side typically, but A and B can be either side. It doesn't matter. Okay, so I'm gonna use the 30 feet, so I'm gonna use this C function and I'm gonna use this A function. Those are the two I'm gonna use. So I'm gonna write this one first as 8 foot over the sine of what? 27, opposite of the 8 foot is 27. And then I'm gonna set it equal to, and I'll use this C function out here. 30 feet over the sine of what? C. And I'm gonna put that C in right here. So that's my over 90 degrees angle, right? It's opposite of the 30, C. Make sense? You good? So far, so good? All right, how do I solve that? Algebra is the answer to that question. Anytime I say, how do you solve that? You'll probably say algebra. Or at least you'll think algebra.
Multiplied by sine C.
Yeah, so our goal is to get C by itself and on top. Like, we don't really want 1 over C as a solution. We want C, right? So somehow we need to get C up above and by itself. There's a few different ways to go about that. I'd move C right away just to get it on top. So how do I get C on top? I multiply by C, sine C. Right, and then those cross, and then I multiply by sine C. So what I do to one side, I do to the other. Everyone good with that move? Okay, and I'm showing the algebra long form. It's a good strategy for you too, if this is not like super simple for you. Now what do I do?
You divide by 8 feet over sine of 27.
Yeah, so I want the sine C thing all by itself, right? So I want to get rid of this thing. What is that? It's a number, right? Yeah, turn it into a number, and then we're gonna divide by it.
My math teacher, told me if you divide by a fraction, you could swap it.
Yep.
and then
Yeah, there's
multiply it.
shortcuts. I'm not going there yet, but there's definitely shortcuts. I'm just gonna stay with the very long form right now. So I'm gonna turn this into a number. 8 feet divided by sine 27. So somebody give me that number just so I don't muck it up.
17.62.
Yep, I agree. 17.62151412. That's this number, right? And I'm gonna divide by it because I'm gonna divide by it over here. So I'm dividing by the 17.62 yada, yada, yada. Which means I have to divide this side by that also. Right, so that's the 30 feet divided by that number. So I'm gonna end up with sine C equals 30 feet divided by the 17 number. I get 17.0246.437. Anyone else verify that? Okay, great. We want the engineering firm to agree on numbers. That's a good thing. And we're all going down together if we got it wrong. All right, now what do I do? So I need C. Angle C is what I'm trying to get. Divide by sine, exactly. Divide by sine, which means this is the same as arc sine or sine to the -1 of that number. Anyone get a number? What's your calculator telling you?
I got confused.
Is it degree in radian?
Huh?
Degree in radian?
No, it doesn't like this number. What doesn't it like? Mine doesn't like it. What's yours giving you?
Yeah, arrow.
Error, yeah, it's like, what? 1.7? Right, that's what we ended up with, correct? Non-right triangles are trick, like they can be really a problem. So. The question is this possible? That's the question. If you're in AutoCAD and you drew 30 feet and 27 degrees, and can you find a distance here that's 8 feet? Right? Maybe the 8 feet's down here, maybe the 8 feet's up here. That changes this angle. So the question is, these three numbers have to work together. And I just made it up. I just threw the 8 foot in, right? Like that was right. Well, the 27 and the 30 is creating a number down here that's not 8 foot. So the 8 foot, the 27 and the 30 doesn't work.
I was going to ask you that. The eight
Yeah,
is
so
actually-
let me show you why. And I always show this because I want you to be aware that non-right triangles can be a problem. Because they can be always drawn two different ways. See if I can do this. Yeah. So here's 8 feet. Here's some angle, let's say 27 degrees. But this 8 feet can be drawn here. And it can be drawn there. So there's two possible solutions. When you have 27 degrees, 8 feet over here, that 8 feet could be there. And this still could be correct. Follow me? That's the problem with non-right triangles, is there are two possible solutions in very specific situations. And the situation is this, where the two sides are not on both sides of the 27 of the angle. In other words, this is down here, this is over here, and that's here. Those numbers have to work perfectly because they define themselves. Okay, if the 27 is here, the 8's here, and then this is known, then this is gone. It can't be true, right? It has to be in this position. So there's something called side, angle, side. And that's what you have to have. You have to have side, angle, side. Meaning that we got to know side, we got to know the angle, the side, and the side. And then that works with the sine law. If you don't have, if you have like, this is side, side, angle, right? Then that would lend us to the cosine law. Because the sine law failed us. And you know that if you trust your calculator. Like if you're putting in a number and it's like invalid, 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 it's like, oh, what the heck? That you can't take the arc sine of something greater than 1. It's not going to do it. Your calculator hates it. Think if you put 9 in, 0.9, and then go arc sine. Oh, no, it won't do that. Oh, no, add a bunch of stuff. 0.9 arc sine, it'll do it, 64. But like 1.1 arc sine gives you that, right? Gives you error. So anything less than 1.9, 0.9 arc sine, it'll give you an angle. Even 0.99, I'm pretty sure. Yeah, 81 degrees. Anything over 1, you're not gonna be able to take the arc sine. Doesn't work. All right. So that means if we had, let's see here, let's just do this again. And I'll put 27 in here. And we had 30 feet, and let's put our 8 foot here. Now I have side angle side. So that's an indicator that the sine law should work. So that's the SAS thing, if you've never heard that, side angle side. So we should be able to go and say, okay, we can make this A. We should be able to get that distance and then work our way through the problem. So let's set it up as A over the sine of 27 degrees. Oh, this is not gonna work either because we don't have enough info.
We have to
Definitely use,
another triangle within the triangle.
you could use, you should be able to use the cosine, the cosine. So C squared equals A squared plus B squared minus 2AB cosine C. Because we know two sides and we know the angle. So this would just give us this opposite side. Right? So this we don't know. That we know. That we know. Yeah, I don't think that would work either, because this is the opposite side.
I think you will have.
We would need this angle.
Yeah, you would need to create.
Yeah,
a-
we'd have to go out and get more info.
Create a triangle within the triangle to find that one, yes.
Yep. Start to build it together. Yeah. Good times. All right. So this one needs 3 sides and you can find an angle, or it needs 2 sides and C. So if we were gonna break this into a right triangle, still not gonna help get that distance. This would have to be the unknown. This would have to have some value too. I'll make it short. 7 feet. Yeah. Let's look at one that's in the book. Let's look at a non-right in the book. Rather than make it up. A lot of them set up and then they can just break them into right triangles. So let's look at 6. So we're 12 feet tall, 16 along the base 3 times. And then we'll go for this side, BC. That'll set up a non-right triangle. You could break it into right triangles, right, and solve it out. Let's just do it with this whole length here. $48. So we have 48 feet and we have 12 tall and 16 here. So we're gonna need this side. I'll call it AB. So we'll get that from a right triangle. Right, and then we have 48 here. We should be able to get BC this long side. And that would be 2 sides. And we should be able to work it through. Could be sine law though. So we'll see. So to get BC this full length, we're gonna need this angle and this side, which we can get from a right triangle. And then once we have this side, this angle, and this side, we can go for this long side. Just breaking it into pieces. So how can we get this angle? Opposite over adjacent, which is tangent. So we're going to use a right triangle first. 12 over 16. Right? This one. Six. Anyone else get that? 8, 6, 9, 8 keeps going degrees. And then AB. Yeah, we can get that from the squaring 16 and the 12. That agreeing theorem. $20. Now we have this triangle. So we use the right triangles to develop the 20 feet, the 36, 8, 6, 9, 8 degrees. We have 48 feet. And then we have a B. BC. Yeah,
The far right triangle,
you sure could.
and then just times it by,
Yep.
or I did 16,
Oh, you did this one down here?
yeah.
Yeah, you could do that one, but you don't know this height, do you?
It's
Okay,
the-
yeah. It's assumption, yeah. But you could also do the big triangle, couldn't you?
Yeah.
Yeah. Yeah, so if there's ways to work around the non-right triangle, yeah, you can go for that. So that just means drop a vertical right here. And we know that vertical is 12. So now we have a triangle that's set up 12 feet. This distance, which is 32 feet. And you could just do Pythagorean theorem again. So yeah, dissect them. Break them into right triangles if you can.
That's the use.
Oh, it's always the easiest. Yeah. And it's when we get into vectors that we won't have that information. We'll be able to do it, but that's all right. We'll go down that road when we have to. All right. I think we're good. I think you definitely have enough for the first homework set, so. Get that done, have it done beginning class Wednesday, and then we'll go over it and continue on. Nice job. Welcome back. Good luck. Stay in touch.